I'm Jake. I work on TypeScript at Microsoft. Just as a guess, how many of you know what TypeScript is? By hands? Oh, thank God. Okay, woo. All right, so it's been a great day of talks. Thanks for sticking around for one more. So I think I'm just gonna get right into it. What is TypeScript? Well, in short, it's JavaScript, but with types. TypeScript is a superset of JavaScript with a rich type system and tool chain. And of course, it uses the types that you have to find the bugs before you actually run your JavaScript. TypeScript has lots of goodies, generics, union types, conditional types, map types, probably other types I'm forgetting about, and I'm not going to talk about any of them today, so don't ask me about them, please. But again, TypeScript is just JavaScript. What TypeScript does is it takes the TypeScript code that you write, verifies it, and then writes out that same code as plain JavaScript so you can run it in places like Node, browsers, etc. TypeScript launched back in 2012 with the promise of allowing for the development of application-scale JavaScript code bases. I think it's safe to say that before TypeScript, JavaScript at scale was pretty much like really rough. Hopefully everyone can agree with that. And my favorite fun fact is that TypeScript was actually the first open source project on the Microsoft org back in 2014. Since then, TypeScript has grown more than we could imagine, becoming one of the most popular languages out there. Currently, it's at number 3 on GitHub, behind Python and JavaScript itself. Last year, Python beat out JavaScript, but TypeScript and JavaScript together are the biggest. And I think that JavaScript losing second place is probably our fault, because most JavaScript devs are actually TypeScript devs. Last year's State of JS survey asked thousands of people how much time they spent writing JavaScript versus TypeScript, and only 8% of people said they didn't write TypeScript at all. But the thing is that all TypeScript devs are TypeScript devs too, because TypeScript is the thing that powers editor support for JavaScript. If you have a hover, that one's us. If you have completions, that's still us. Syntax errors, even in files that have no types in them, that's us too. The TypeScript toolchain is what makes all the features work, be it in TypeScript or JavaScript. Now, like most languages, TypeScript is written in TypeScript. That itself is not unusual. Most languages are written themselves. I mean, Go became self-hosted in 1.4. But since TypeScript is JavaScript, like I said, what's unusual is having a compiler written in JavaScript. You know, there's a tremendous benefit to being self-hosted, absolutely. We get immediate feedback on our own code. We know if this is broken, we can fix it. If something's broken in the editor, we fix it, right? And we get the feedback immediately. Our community knows TypeScript, obviously, and so they can send us fixes. And then it's all great. But there are, of course, challenges. Believe it or not, JavaScript wasn't designed for writing compilers. The language is much more designed for writing code for browsers, DOMs, sandboxes, and as efficient as JavaScript runtimes are, which they are really efficient, there are still inherent overheads in the language. You can't share objects between threads, so if you want to do multi-threading, you need to serialize data back and forth, which often defeats the whole purpose of the thing. You have to write async await, which means the function coloring problem, love that. And there's a non-zero cost in just allocating all those promises all the time. And even worse, many builds of JavaScript runtimes have a memory limit. So for example, if you open VS Code, it uses Electron, and Electron has a 4 gig memory limit, which causes problems with people with massive code bases. And to be fair, we squeezed as much as we could out of the language. We had lots of profiling, work skipping, caching, monomorphization. I'm not going to get into that one. It's JIT optimizations, right? Writing our code so that runtimes can run it better. But we still have performance woes out of memories. And since people's code bases are only getting larger and larger and larger, the problem just gets worse over time. And of course, we make the language better, but every type check we add makes us slower. We're checking more things. Now, to be clear, JavaScript as a language is always improving. There's a saying, always bet on JavaScript, and I think that's still true. But with the way things work, even if a lot of this is fixed, it's going to take a very, very long time for us to actually pick up any of those changes. So last fall, we started asking ourselves the question that everyone had been asking us forever. Could we rewrite TypeScript in another language? This is something that we said no to for a long time. We just kept working to squeeze more and more out of JavaScript. But at a point, we're just hitting enough walls where we want to try and prototype something else. Now, obviously, there's a lot of language choices out there. I put up 5. You can list a billion more. Rust is popular. You know the meme, rewrite it in Rust, right? And there's a trend of rewriting writing tools in JavaScript in Rust, or at least including Rust in your code somewhere. Go has precedence by ESBuild, which I would credit as the pioneer of JavaScript tools written in a compiled language. One of the newer JavaScript runtimes is written in Zig. That's pretty cool. Flows compiler is written in OCaml. And obviously there's C#, which at Microsoft has heavy investments, node bindings, it's cross-platform, et cetera, right? So let's go through some of the requirements that we would have for this kind of rewrite. Obviously, we're going to rewrite another language. That language has to be fast. We want to compile the native code, and that's fast, right? And we want for support for shared memory concurrency and multi-threading, so we can actually use all the cores on your system. In JavaScript, we get the single core, more or less, right? We also want to make sure that whatever we build is cross-platforms, because JavaScript can run basically anywhere. So we need to make sure that we still are able to run people's code, and that includes places like WebAssembly for the browser. But there's another key gotcha here, which is that TypeScript doesn't have a spec. Many languages have specs. Go has a spec, but many don't. TypeScript is one of the languages that only has a canonical implementation. The spec is just whatever the 150,000 lines of code in our core compiler do. People depend on obscure behaviors, whether or not we even know that we have them. It's like Hiram's Law, but worse somehow. And the thing is that even if we had a spec, there could still be other behaviors that our users depended on. So for example, I mentioned that TypeScript has union types. The ordering of the types inside those unions is undefined. If we wrote a spec for TypeScript, we might be tempted to also make that undefined and say, yeah, it's up to the users to solve that problem if it actually matters. Now, to be fair, there used to be a spec a very, very, very long time ago, but it hadn't been updated a long time, and I deleted it after people kept asking questions about it. And you can see it's tiny text, but like we put archive, we put deleted, we put all these notes in to say, please don't read me, and then we just deleted it because it was too late. Okay, but the thing is, so because we don't have a spec, we can't rewrite the code base. We have to port it. We need to take fundamentally the same code base, plop it in another language, and then preserve as much as the original behavior as is possible. So if we add to our list of requirements, now we're saying our code needs to be porting compatible. It needs to be actually possible to take the code and plop it in this language. So first off, that means that we have to be structurally similar to TypeScript. This comes down to superficial stuff like curly braces, sure, I guess. But mainly it's about the kind of patterns of the code that you write. In TypeScript, we don't actually use classes at all. We have none of those. We all have functions, interfaces, and data. We also need garbage collection. JavaScript has garbage collection, so we end up just creating a whole bunch of objects all the time. And more importantly, we have so many things in our language that are cyclic. We have ASTs where we have parent pointers, so we can go down the tree and then back up the tree. Types can be recursive. And so it seems infeasible to do ergonomic cyclic data structures without garbage collection. And then finally, the language needs to be easy to learn. So we have a team of people, they've got to get up to speed quickly. We actually want to finish the effort, right? And we don't want to have it be too complicated for our external contributors that need to come in and contribute to the language. And so all signs are pointing one language. You knew that already. We're at GopherCon, right? Go. All right, let's type. So first off, we start from the bottom. We're starting from the bottom, starting up with the scanner and the parser, scanner or lexer, depending on how you call it, the very bottom. Meanwhile, a few of us are futzing around with other languages just to be sure, right? And pretty soon, we found that our parsing phase was 5 times faster out the gate. It was just the same code, one-to-one, plopped into another language. And that code looked extremely similar to the original TypeScript code, proving that this just might be feasible. So let's get a rough idea of what the porting process looks like. This is just a random snippet of code. And our old code was class-free. So we have functions, and then we close over state. So you can see here these consts that have maps and types or something on the top here. And then we write our functions inside the outer function, and then return those functions as some sort of API. Believe it or not, this is the fastest way to do it in JavaScript. Otherwise, we would have done classes or something. The effect of this is that our type checker file has 65,000 lines of code in it. You couldn't view it on GitHub. But it was as fast as we could make it, right? In Go, though, we can more simply write plain structs and methods. The code looks pretty similar, right? We don't need inheritance, polymorphism, all that stuff. It's just data and functions. And so early on, while the scanner and parser were being ported, I wrote a tool that does this. It loosely transforms TypeScript code into Go code. TS2Go uses TypeScript API to parse it, then converts the TS syntax to Go using type information to write down types as you need. So for example, for code that looks like this, TS2Go will turn it into this. Same thing, right? If you have code that looks like this, a little more complicated bitwise operators, some type assertions, it turns into this, right? Corporate needs you to find the difference between this picture and this picture. It's the same picture. Now, it's not all a perfect one-to-one. The output might not be syntactically valid. I didn't code for that. And so you can see here, I have a piece of code where there's an or. In JavaScript, that means take the left value if it's truthy, which means, and then you take the right side otherwise. In Go, that would have to be an if statement. So there's a bit of manual massaging required here. Now, Go also lacks a ternary operator, and so that turns into a fake if-else function call. Note that this is not necessarily a trace-safe transformation. You can see here that there's an argument that's always get evaluated here. So this could cause a side effect. And so again, you needed a little bit of manual intervention. Another pattern we used heavily in our old code base with these sort of match case, nested ternary operator expressions. TS2Go detects these and then turns them into switch cases. So it's a little less concise, but it is equivalent. So with TS2Go in hand, we started porting more and more code. Pretty soon, the binder was done, the checker was done. Don't worry, I'll define those later. The perf continues to be great. We're getting 3 to 4x single-threaded. And of course, you throw in concurrency, and now we're over 10x. And this is Go, so adding concurrency was what, like 5 lines of code, right? And at this point, the effort is undeniable. So it's time to bring in the rest of the team. We have 10 engineers roughly on the team learning Go for the first time. I think I was the only one who had meaningfully written Go before then. And a lot of people on the team, well, some people on the team have only worked professionally in TypeScript. But the learning period was pretty short. There was a bit of teaching involved, but Go is a simple language, right? Mainly the advice was like, please write simpler straight line code, don't go crazy with the channels. And soon after, we had a virtual file system, basic CLI, file loading. Each step unblocked more work. And then we're finally to the point where we're all working on different things, like testing, CLI, file watching emit, and so on. Fast forward a couple of months, and we made up enough progress to test a few big projects, and the performance boost holds. So VS Code's a 1.5 million line code base. Previously, it took, on my machine at least, about 80 seconds to compile. Not great. And now, it took 7 seconds in the early iteration, right? And the same speedup applies even for smaller projects. So we're pretty happy with that, right? Fast forward a bit more, VS Code was compiling cleanly this time. The old code had errors. We get everything looking good, and we announced it on March 11th. The reception of this was overwhelming, to say the least. I think many people were flabbergasted. The YouTubers, oh man, they really loved it. And of course, as we expected, most questions were why we didn't rewrite it in blank, Rust, C#, Zig. Nobody said C++. Lots of Reddit threads, Hacker News, Twitter, etc. People commented on our release blog, so which means that they scrolled past the explanation just to complain. But thankfully, some people in our community really understood what mattered. Could our type system still run Doom? Our type system is currently complete, so it can actually run Doom. This came out a week before our announcement, which is very funny. So you can look that up later. Now, the excitement didn't limit itself to the TypeScript community. The Gophers were excited too. Right away, Go contributors were testing out our code. On the same day that we announced, someone filed a bug on the Go compiler saying, the Go compiler is slow compiling the TypeScript compiler. 2 days later, we become a Go compiler benchmark. That's pretty sweet, pun intended. That's a joke for the Go team. Later, there's a pair of CLs that sped up the compilation of our checker package by like 5x, and that's in Go 125. That was relieving. And so like Filippo says, with all that support, why pick Go anyway? Oh, okay, you can read it, sorry. I don't know if Filippo's here anymore. All right, okay, but enough about reaction. Let's about the reaction. Let's get into the details. It's the reason why you're all here, right? One of the main reasons that we were so successful in porting the code base was due to our extensive testing. TypeScript is nearing about 100,000 tests. On my machine, I'm very lucky. I can run those in 2 minutes. In CI, it's more like 15. A significant number of tests are in the form of compiler tests, where we write out some code, and then the test harness runs the compiler on that code, capturing baselines. For example, we create type baselines, where we walk every single node in the AST and ask, what's the type of this node? What's the type of this node? What's the type of this node? And we write that out, storing the result. If we're working on a change to the compiler and we break something, we'll know because one of the baselines changes. These files are committed to the repo, so we can review them in PRs too. Baselines are sometimes known as snapshots or golden files for people that don't know the term. We also do the same thing for error message, so we get this really nice squiggle output here for errors. Those get baselined. And we get it for emitted files. So you can see the difference between printing out the TypeScript code and printing out the JavaScript code, again, is there's no types in the JavaScript code. But the key part of this is that we can re-implement that same test harness in Go. We can run the same test against the old compiler, or with the new compiler and the old compiler, and then diff the baselines. We can even commit the diffs as even more baselines, and then slowly, as people fix things, delete the diffs as we're improving the situation. That was the main way that we could track progress and figure out what to focus on. Sometimes we'd send a PR, it would fix a couple baselines. Other times we'd fix something and it would like 500,000 lines of baselines get deleted, which was pretty great. And now in the new code base, the tests run a whole lot faster. My machine can run the whole thing in like 20 seconds, which, yay. In the process of the port, though, we had to think about data layout, as Go and JavaScript, of course, are very different in the way that they represent objects in memory. For our AST, the abstraction text tree, the most obvious layout is a node interface with individual node types implementing it. But this has a couple downsides. Within the AST, we store a huge number of references, and those often appear as node interface values. Interfaces are fat pointers, so that's actually 2 pointers, right? Now, in terms of scale, if I compile VS Code, that is about 9 million nodes that we're allocating to do that. And VS Code is 1.5 million lines of code, and we know of repos that have 15 million lines of code. And if you do the math, maybe it's not that much, but what's worse is that most of them are actually nil, only there just in case. So for example, if you have a bunch of if statements, most of them don't have an else at all. And so we're spending memory on things that just don't actually exist. And then worst of all, the worst thing ever, is that we just kept assigning nil pointers into interfaces. That's a classic Go bug, right? And in TypeScript, that's not a problem, because if I have type A and type B or undefined, I can assign them to something else, and the undefined just persists. It's all sort of on the top level, because the type system doesn't exist, it's just undefined or it's not. Further, we sort of had this odd dissonance between some of the specific type fields and node fields. Sometimes you'd have a node, sometimes you have a specific type, and so you try to write a helper that works on one, and then you find out that you have to refactor it into the other one. Other times, we need to change our AST, and you have a child that was previously one thing, but now it needs to be 2 things, and so you have to change the type, and then it cascades up through your call chain. And that was pretty annoying. And then finally, one of the other friction points was having slices of nodes. You'll note that the 2 slices for these child nodes, for function declaration and call expression here, are different between the 2 structs. These are the most specific types we can have, so they're arguably correct. And that's great for safety, but the effect is that it's really, really hard to write code that works with multiple slice types with different nodes. Generics can help in some cases, but it can't help in others, like local functions, or you have to declare the top level thing, and that's its own thing, right? And we ended up, in some cases, we still had to do copies, and that just didn't feel great. If you search out array covariance, you can find a better article about it than I could ever describe here. So early on, we switched to a completely different AST representation in which everything is a struct. The base node struct contains the common fields that we always need to access, including the node kind, position, source text, parent, some other stuff. And that base node is then embedded in each of the specific AST node types. If you want to go from the specific type, you just take the address of the embedded node. It's the same top pointer, right? We then only pass around the node pointers, not specific types. We lose safety in these cases, so I'm not saying to do this yourself, but a lot of time we're just passing things around from one function to another, and we're just looking at, say, the common fields like kind. And most importantly, this meant that we stopped boxing nil and putting it in interfaces because we only have one type, the node type. So a whole slew of porting bugs just disappeared. If you have a node pointer, though, you need to get back to the specific type to access the rest of the fields. And so the node contains a sort of self pointer, which is an interface value that points back to the original node. This is set on creation. The node slices now contain node pointers, so we can write code that works across the board against any of them. And finally, since node is no longer an interface, we can have methods on it. So we can define helpers for downcasts, for discoverability, but also helpers to access common fields and do common computations. Now, to be clear, again, this layout is not perfect. There's a loss in safety here. It's probably clear for the average Go project to just use interfaces and do it the normal way. But for this, it was better for our specific port. To allocate AST nodes, we have methods on a factory struct. I know word factory is scary, but it's mainly there for bookkeeping reasons. I've hidden those in the slide. But the methods are straightforward. They just allocate a node, set it up, and then return it. When we profiled our parser, we found that we had a huge number of allocations. Not surprising, but it was like 30% of all allocations during parsing are just identifiers. I think like 13% are just lists of identifiers, or list of nodes. And so in Go, it's not free to allocate memory. You have to call into the runtime to make an allocation. So oftentimes you can try to reduce your runtime by reducing the number of allocations that you make. What we did was that we added a pool or arena, depends on how you define it, whose job it is to allocate nodes. It allocates large slice and then it hands out pointers to each element until the slice is empty and repeats. A downside of this approach is that if any of the items are still referenced, the entire slice will not be garbage collected. But for us, this is fine because the lifetime of every node in the AST is just the same lifetime of the entire AST. So either the AST is there or it isn't, and that's great. It might not work for your application. Pooling the top allocating nodes gives us a 20% perf boost, parsing our massive old checker file, and does 96% fewer allocations, which is a significant improvement. You do pay a little bit for the empty files because you might overallocate, or if you have the factory have more stuff in it, but that's pretty uncommon. And since we have one factory per parser, each file parse is able to do most of its allocations without ever synchronizing with anything else. Okay, now you Go people take this one for granted, but JavaScript does not have value types outside primitive values, so you can't have objects as keys in maps. And so we had to stringify everything. This is not as slow as you might think, I promise. We'll talk about that later. But you can see that we have to sort of stick special characters in there to avoid collisions. In Go, though, we can just use a struct, which is clearer and less error-prone. And composite map keys, kind of like Go, are being worked on for JavaScript, so that'll be great in the future, but obviously Go's had this forever. Another fun difference is string encoding. When we parse files, we hold on to the original source text. JavaScript, C#, Java, probably someone else, all store strings internally as UTF-16. Some JS runtimes are clever and can store ASCII as a smaller representation, but in practice, in our code, the strings were still stored as UTF-16, and we use UTF-16 positions for everything. And yet, basically all TypeScript source is UTF-8. So what we were doing is we would parse out a file, and then Node would decode the file into UTF-16, and then we write it back to disk as UTF-8. And so Go, of course, are UTF-8 strings, and so we can save memory on many files if they have special characters in them, and we can read those bytes directly into memory. Now, getting this to work right was pretty tricky, as we have to audit basically any place we ever do string slicing or position calculation, but the result is worth it on the whole. Now, of course, this wouldn't be a Go talk without concurrency. About half our speedup is from concurrency, and we probably wouldn't have done the port at all if it had not been for shared memory concurrency. Now, to understand how we use concurrency, we first need to look at how TypeScript actually compiles. The first phase in our compiler is parsing. In this phase, we read all the files the user specifies, resolve the imports, parse more files, resolve those imports, rinse and repeat until we're done. The second phase is binding. In this phase, we walk all the ASTs, collect symbol information, do scope analysis, and build control flow graphs. And then we attach that onto the ASTs. Then we check the files, walking each of them, verifying the program is correct. That's a big hand wave for sure. Really complicated in there. And then lastly, we emit the files, erasing the types, transform the syntax so that we support older versions of JavaScript. Now, in the old compiler, we had to do all of this single-threaded. This meant that we parsed files one after the other in sequence until we were finished. And then we bound every single file in sequence until we were finished. And then we checked each file until we were done in sequence. You see a pattern? Then we emitted each file in sequence until it was finished. Surprise. We couldn't do any better than this in JavaScript because there's just no way for us to share objects between threads. If we tried to do these things in parallel with threads, sure, we could parse in parallel, but then we'd have to serialize the data across to the main thread to check the rest of the stuff. And the amount of time it takes to do that serialization is about the same time as it takes to parse the file. So it's not worth it on the whole. But in the new Go-powered compiler, we can do better here. Parsing a file does not depend on anything else. So we can parse as many files as we want. We can do it all in parallel. Binding a file is self-contained, so we can do all that in parallel too. File emitting is also self-contained, surprise, so we can do all that in parallel. But type checking and evaluation is a really complicated process. Information can be pulled from anywhere at any time. One file can affect what happens in any other file. There's global effects, things are order dependent, there's recursion, right? And so the question is, how do you handle concurrency for something like that? So let's push the topic stack again, and we'll look at the checker, how the checker works. Don't worry about reading this, it's not important. Our checker does not work like a traditional compiler where you have to process everything before you can use the information. Instead, the checker is able to pull information on demand, evaluating only what's required to check that specific code. And the information is stored internally to the checker in maps and arrays. But even more critically, you can ask for the types anywhere in a file whenever you want. If you hover over a random node, it'll just look at what's required to provide that hover. We often refer to this as helicoptering, where you can just swoop in randomly on a file and ask for information. When the code changes, we throw away the checker, and then we make a new one and start all over again. Now, because of this design, we're presented with a unique solution to our concurrent checking problem, and that is just make more than one checker and assign each of them a subset of the files. They'll only pull the minimal amount of work required to do the check that they need to do for their subset. There might be duplicated work between the different checkers, but the overall effect is still a net win. All of this together makes a difference between just using one of your cores and using all the cores. Now, of course, the question everyone asks us is, will you switch to concurrency? You're all JavaScript devs. What about the concurrency bugs? And you'd be surprised to learn that we had very little to fix. Our design already had shared and immutable ASTs. That was required to reuse ASTs between multiple builds and when you're typing around in the editor. The checker, we're keeping single-threaded. It holds all of its state internally. We just spawn more of them when we need. And then the emit is embarrassingly parallel, but since emit can depend on things from the check phase for very specific features, we did introduce a mutex to make it race-free. That's not to say we didn't have any concurrency bugs at all. Here's an example where we did cause a race condition. So like I said, our ASTs are supposed to be immutable after creation, but the old code base broke this invariant sometimes, usually out of convenience. And so you can see here that we set a bit on a flag inside the node to say that some cached computation had been completed. And that's fine in JavaScript because only one piece of code is ever running at a time. But when you're porting to Go, we left some of that code in place without realizing. The race detector, of course, did its job, and it told us that we were modifying the node flags concurrently. So we just dropped it. The race detector also caught places where we were mutating our control flow graph. This pattern is, again, fine in JavaScript and for convenience, but it just doesn't fly in Go. And so the code was rewritten to store this information somewhere else. Now, we had more race conditions to this, and the Go's race detector did a great job pointing those out for us. Another key area that we're changing things is the way that we talk to editors. As I said before, the TypeScript toolchain also includes a language server. In the new code base, we're switching to the LSP, the language server protocol. And most people familiar with editors are probably asking, what do you mean? Well, weren't you already using LSP? But no, we weren't. TypeScript predates the language server protocol and has its own protocol that more or less inspired the LSP. And people have been asking us to switch to LSP for a really long time. And we think the port is a great opportunity to do that. One of the reasons is that our old protocol was synchronous, except for the cancellation. This effectively meant that we could only ever do one thing at a time. Your editor would send a completion, it would just do that until the next request, and then we do the next thing. This limitation led to client-side workarounds for this, like VS Code spawning multiple language servers so that like a more bare bones one without a checker could answer requests while the full one was getting ready or working on something else. But the language server protocol is asynchronous, meaning we can do more than one thing at once. And we wanted to be able to do more than one thing at once. That's going to be faster, more responsive, right? But now we're introducing concurrency. We directly ported a bunch of code from the old language server and ended up with a bunch of race conditions. Many of those were caught by the race detector, great. But other ones were more logical races where the code was technically not a race, but a logical race instead, and things just behaved strangely. And just last week, we merged in a change that rewrote the way that our language server works to use an immutable snapshot model, which solved all of our concurrency woes. That's not a new idea. It's used in GoPlease, it's used in Rust Analyzer, Roslyn, but it's new for us. Additionally, our design with disposable independent checkers also aids in implementation of a concurrent language server, since now, if a request comes in that needs to use a checker, and another one comes in, we can just make another checker and throw it away when we're done. Which means that we can serve multiple semantic requests at one time, including like diagnostics at the same time as completions, which is extremely often. Now, earlier I mentioned our special compiler tests. We also have a similar concept for testing editor features. It looks kind of like this. We didn't want to drop any of these tests, so we have a script which converts the old test into plain Go tests. You can see a pattern here. It's a little bit verbose comparatively, but it works. And every one of our LSP tests spawns a full LSP server and it just sends it messages like a real client would. And what's cool is that because our ASCs are independent and immutable, doing the full end-to-end for 1000fs is pretty fast. We can actually share the ASCs between all the different programs and all the different tests because we never touch them. In our original code, we rarely did a real server test because of the persit, but now it's a lot simpler. Now, it wouldn't be a Go talk without some Go gotchas, and we, of course, encountered quite a few during the port. So here's a fun question for you. Can you spot the bug? Oh. Well, the bug is this. There are two declarations named result, but the code intended to return the second one. The real code is just one character away. We have a lot of code like this in our code, and we just kept hitting this bug over and over again. If you're experiencing Go, you're probably asking the question, why aren't you returning early? I agree. That's not the way the code is written or reporting it, right? And so the bug happens so often that I wrote a Go analysis analyzer to catch this. I'm not going to go into bigger details here, but the Go team has a similar analyzer called Shadow. But I found that it had too many false positives in our code base. So the new version uses control flow analysis to only flag cases where shadowing would actually have an effect on the runtime. It'd be pretty cool to upstream this at some point. And after enabling the analyzer in a repo, we just never had a shadowing bug again. Success. Now, if you remember our old code base, our code looks something like this. For example, this binder closes over data and functions. In this bit, we're binding all the children of a node with a for each child helper function. In Go, the code is very similar. The only difference is that we're using methods instead of local functions. But when we profiled the code, pprof pointed out a problem. This code has a lot of allocations. Well, why? The compiler can't prove anything about what for each child does. There's no inlining, it always escapes. And so the method value gets recreated every single time. This is an operation that looks cheap on its face, but it's not cheap at all. We fix this by pre-binding the method, maybe it's JavaScript terms, but we store this, store the function up in a field when the binder is created, and then we call that field instead. And so the result of this is that we improved the performance of our binding phase by 17%, which is like 90% of our allocations. Another similar example is our parser, where we used to have a lookahead function. You'd give it a callback, and it would speculatively parse some code and then return result and rewind the parser back to its old state. In some cases, we would pass in a local function, which necessarily accesses other state in the parser, which means that in the Go code, it's a method. But since the lookahead is a method on the parser, we can instead pass in a method expression instead of a value. Since methods are just syntactic sugar for a function with the first argument being the receiver, you can just explicitly call it with the parser as the first argument. This isn't needed in every case, but sometimes the code can't be analyzed by the compiler. Okay, here's another one. In Go, this is a big no-no. Every time you concatenate the string, a new string is allocated. You're supposed to use strings.builder. But in JavaScript, this is actually totally fine. The runtimes optimize this. In V8, it's called a con string, which is some functional programming language jargon, but it just means there's a tree of strings. In this case, we're always appending, so it looks like a chain. And so strings that are joined with plus, join, and so on aren't flattened until they're observed. Hashing doesn't have a flatten either. It just walks all the different strings. And so those stringified maps that I showed you earlier are actually efficient because querying the caches doesn't actually reproduce the entire string. It just hashes the con string. But the fact that we did this in Go led to perf bugs in Go, perf bugs in our TypeScript port to Go. And thankfully, pprof will point this one out for you. It'd be really cool to have this feature in Go, but I have no idea how that would work. And of course, the biggest friction of all were the language features we left behind. And that's, oh boy, here we go. Nil safety, love that. Nil coalescing, lots of question mark, and question mark dot in our code base that now have to be if statements. We had to fix a lot. We had to turn our union types into just boring types that are interfaces or just the node pointer, right? Generic methods, we had a lot of those, turn those into top-level functions or just give up. And ternary operator, which there's an FAQ entry about, so I don't think that's happening. But it's okay if we go through some pain because what we want is for TypeScript to be faster for our users. Okay, so where are we today? We put out a preview build a few months ago. It's even more feature complete than it was today than it was then. Editor support has been constantly improving. We have build mode for multi-project situations that was merged also last week. Last week was a really good week. Our preview package is getting another 20,000 downloads. I'm not sure who those people are, but they're using it. And some big TS users have already switched over. So like Slack, their build used to be, I think, roughly 6 minutes. They're now it's down to 40 minutes. So it's like 9 times faster. That's really good. Figma just got it working last week too, and they're seeing about 5 times faster. So maybe we got a profile to figure out where the 10x goes. And VS Code is starting to use it to build some of their stuff. There's also a linter being worked on that uses our code to implement typed lint rules that previously used our compiler APIs. The new linter ported the rules into Go and got something like a 30 times speed up. And that's apples to apples too. These two examples have the same exact configuration before and after. Of course, it only took the most cursed hacks possible to do it. Even when we switch languages, the TypeScript ecosystem finds a way to pull on our internals. It's never ending. What's next? We're pretty far along in the port. There's still a lot of work to do though. We're working on a bunch of great stuff. A lot of our efforts are being spent on the editor functionality. There's stuff being re-implemented currently, so auto imports are coming soon. Rename, I think, just got merged while I was sitting over there. The rest of the LSP, of course, as well. That big language for refactor also means a more straightforward path to implementing speculative edits, so we can check if a code action will work or not. Refactors like that, or even MCP. We're finishing up our emit transforms. In the future, we're going to work on like file watching and contributing back to the LSP all the special features that we used to have in the old TS server. And hopefully those features are also useful to places like Go. For me personally, I'm excited to get WASM going and figure out how to use WASM faster. I would like to get a Go API out there. People are asking for that one, but that'll be a challenge because of the Go 1 promise. So we'll have to think about how we're going to do that one. And of course, we're always working on perf. All being said, we're still iterating on the main TypeScript code base, and so TypeScript 6.0, our next release, will include a bunch of deprecations and changes that help smooth over the transition to TypeScript 7.0, which is what we're going to call the one that has Go. So in summary, the future is bright. We're really excited to continue this effort. Go is a huge part of that, and I really think Go has been a great fit for the port. It's also been great to talk to the Go team and cross-pollinate ideas. We've had many conversations, especially this week, and I'm really excited for the future.